it again. It's fabulous data. So Hannah Übler is next as part of this sequence, and Linda Taccone says that she's giving 5 minutes of her time to Hannah. So I'll give you
Thanks, Linda.
10 and 5 minute warnings.
Yeah, good morning, everyone. I'm very pleased to be here. Finally, it's this famous conference in this beautiful Santa Cruz campus. And as Reinhard said, I will continue on a few of these topics that he brought up already. Particularly, we'll talk a bit more about individual rotation curves at higher redshifts, and then move on to the Tully-Fisher relation of redshift 1 to 2. So Reinhard showed us some impressive results from H-alpha rotation curves. And of course, you can ask the question, how does this look in other gas traces? And as Raymond already introduced in his talk yesterday, in simulation, we often find that the young stars in the gas, the molecular gas, trace each other very well. And he already showed actually this example from one of Reinhard's paper. So this is a redshift 1.5 galaxy where we have H-alpha and CO data which trace each other very well. You can see this here in the H-alpha field intensity to the left and the CO velocity field to the right. And along the kinematic major axis, we find the 1D rotation curves in H-alpha and CO in the upper right, which within the uncertainties agree pretty well. But so to determine a robust dark matter fraction, this galaxy is not optimally suited because we see here this mass distribution in the southeast, in the UV optical, as well as in the H-alpha and CO. And if you look at the velocity fields there, the difference in velocity suggests that this is, there's a minor interaction going on. But we have now acquired data for another galaxy in H-alpha and CO. So here we have a redshift 1.4 galaxy. Show you again the velocity field. So these are in CO, 60 hours with Neumann at the Plateau de Boer, and 21 hours with Lucy at the LBT for the H-alpha PV diagram that I show here. And we can do the same exercise and cut along the kinematic major axis, and this gives us then the 1D profiles in velocity and velocity dispersion. And here you can see that these agree remarkably well, especially in the rotation curve. In H-alpha is the yellow and CO is the blue. You see how these go together very well. And due to the quality of the data, we can expand our analysis a bit, and we can cut in the PV diagram spatially to trace these high velocity peaks that we see in the outer parts right into the center. So these are the open points that you see now on the rotation diagram. And this suggests that there is a significant distribution and concentration of baryonic mass right in the center. And in fact, if we try to fit these galaxies with the models that Reinhard already introduced, so a disk, a bulge, and a dark matter halo, and if we let some of the parameters free, so in this example here, the baryonic mass, halo mass, and the bulge to total ratio, indeed, we find a very good fit with a high bulge to total ratio of 40%. And you can see if you look at the intrinsic rotation curve that we get from the models here, how the central bulge is a very prominent component here, and actually very well traces these open symbols that we have from this analysis technique right in the middle to the center of the galaxy. So now we can look at our model and the effective radius of the galaxy, which is 0.5 arcseconds in this case. Look at the dark matter fraction. This would be, with this model, 26%. We can use this to place this galaxy on this plot that Reinhard already introduced. So we have here the dark matter fraction and disk tail length as a function of the circular velocity at this radius. And Reinhard didn't have much time to show this. So here are the 6 galaxies from Nature paper with very low dark matter fractions close to the location of local early type galaxies in this diagram. And the new galaxy that we have here in this orange-blue falls close to its lower redshift examples from Reinhard's paper. And now, of course, the question is, where do these low dark matter fractions in the centers come from? And we already heard yesterday about a few things that can be a cause of this, like halo expansion due to outflows. The concentration parameters could be lower. The dark matter profiles could be different. So as Reinhard said, we're using NFW here, but we heard also already yesterday that other profiles might give a better fit, and often they allow for a halo which has more mass concentration outside. But one thing that is for sure is that we see very high baryonic concentrations. So the relative fraction of baryonic to dark matter is very much dominated by these strong concentrations. And you can look at this also from a point of view that Sandro Keller took in his 2015 paper. You can look at the surface mass density as a function of radius. So the black lines in this diagram are Reinhardt's galaxies. The red line is from Sandro's paper, local early type galaxies that are mass matched to this sample. And then in blue-orange, we have this new galaxy. And you can see that these higher redshift galaxies have baryonic surface densities that are close or even exceeding these of the quenched local counterparts. And this suggests that the centers of these galaxies have very much evolved already and have these very high baryonic concentrations that lead to this comparably low dark matter fractions. Okay, so this was no individual galaxies, and in the second part of the talk, I would now like to, thank you, change a bit the focus, go to the Cambridge 3D sample and increase with this the sample size. Reinhard already said a few words, so here to the right, I give you the selection of the Cambridge 3D sample. From the first 3 years of data, Stein-Woutz made an analysis that gave this beautiful plots that we have here. He selected 240 galaxies with high signal to noise that were also showing in the rotation field these signs of ordered disk rotation. And he made a kinematic analysis with a thick disk model, and of course also taking into account the pressure support, as we know also from Susan's work and Raimund's work, how important this can be at high redshift for the kinematics. And by contrasting the stellar and baryonic masses of those galaxies to the inferred dynamical mass from the model, he could then contrast this to get baryonic mass fractions. And he was finding that these high redshift galaxies are dominated by baryons by about 50% on average, but also that this fraction increases with redshift. So that if you go to redshift 2 or greater, you find baryon fractions that reach 90%. And of course, this is in line with many other recent studies looking at baryon fractions in the community, so we agree in this pretty well. Now, from these 240 galaxies, we down selected 135 for an analysis of the Tully-Fisher relation. In particular, for the selection here, an important point was to take only galaxies where we see a turnover in rotation curve to be sure that we trace the full dynamical potential, because as you know, the virtue of the Tully-Fisher relation is that you can actually connect an observable, the stellar baryonic mass, with the potential of the halo, which is in itself something that we cannot directly observe otherwise. So this was a very important cut. Then we selected rotation-dominated systems, and then, of course, Raimund pointed this out yesterday, one has to be careful about close neighbors. So naturally, we try to do as best as a job as we can here right now. We do not only look at the morphology and kinematics, but also segmentation maps and the neighboring catalogs of the 3D HSD sample, such that we exclude all galaxies with close neighbors that are closer together than 20 kiloparsecs. So, and try in that sense to mitigate these issues that can arise in the kinematic interpretation of these galaxies. So here to the left, you see now the stellar mass Tully-Fisher relation that we find from the Cambridge 3D sample. In blue, redshift 1, and in red, the redshift 2. And you can see that those galaxies populate the same space in the Tully-Fisher plane, but they're offset from the local relation, which is here shown in black by Reyes 2011. And as you know, of course, in the last 15 years, there have been many studies of the high redshift Tully-Fisher relation, and most prominently in this audience, of course, Susan's and Raimund's work also on this same topic. We can also look now at the baryonic Tully-Fisher relation, which you see here to the right. And immediately you can see that the higher redshift galaxies in red are offset towards higher baryonic masses. So on the one hand, this emphasizes the importance of the gas fractions that are increasing with redshift. If we look at these two galaxies, for example, with similar stellar masses, but very different baryonic masses. But then again, for those galaxies to land in the same space in the stellar mass Tully-Fisher relation, something else has to take up this dynamical support for the lower redshift galaxies. And this, we believe, is dark matter. And indeed, if we take into account the dark matter fractions that increase when we go towards lower redshift and the gas fractions that are decreasing, we can build a toy model of galaxy evolution, Tully-Fisher evolution, that matches fairly well to a first order these trends that we see in observations. So what you see here is a typical Tully-Fisher evolution plot. We have the 0-point offset on the y-axis as a function of redshift. The stars is the stellar mass relation from KMOS, and the blue square is the baryonic mass relation that we find. And just to make this clear, if we would have a relation between mass and velocity that would depend only on the evolving Hubble parameter, we would expect a relation like this, as you can see in many, thank you, in many of the semi-analytical models, for example, by Dutton and so on. But if we, in fact, take into account the fractions of gas and dark matter that are also dependent on redshift and evolving, we find these green lines that show the same qualitative trends as the observations that we have. Now, you also know that in the Tully-Fisher community, there is considerable tension if there is now a 0-point offset or not with redshift in the Tully-Fisher relation. So here I'm putting up a few studies, and there are, of course, more that I've not put on this plot here now. And you see that there's a number of studies that agrees pretty well with what we find here. For simplicity, just showing the stellar mass Tully-Fisher relation, but there are others that are not. And the question is, of course, why is that the case? There are a number of reasons that one can investigate. So let's just quickly go through a few things. One is to first order the measurement of the masses. So this is, for example, the study by Di Teodoro, which uses KMOS3D and cross data. They have already in the estimation of the stellar masses factors by up to 0.5 dex. And then it's no surprise that we cannot find the same relation. Then, of course, the dynamical models and the velocity measures, which I've highlighted here, different colors. You see this is all over the place. But at least for velocities that are measured from the emission lines, all those values are usually at the point where they're measured in close enough agreement that this cannot explain this huge offset. Then choice of slope can be important when you compare to studies. If you account for the pressure support or not, for example. So here, this green points, the open stars is if you do not take this account, and then the filled stars if you take this into account, and you see at high redshift how the pressure support can become a very important correction. Then sample selection. So we made a test if we include in our sample also all the dispersion-dominated systems or galaxies where the rotation velocity is underestimated, then we are consistent with basically no evolution. So this can be a very crucial point, and depends, of course, what exactly you want to achieve with your Tully-Fisher study. And then also statistics. So we also have 22 galaxies at redshift 1.5 that we did not include in the paper in the Tully-Fisher study because we were finding that this was too dependent of those galaxies, which you would pick, what the slope and the position of the 0-point offset would be. So this is also something where you have to be sure that you actually sample the parameter space well enough that you can determine this. And then, of course, slit versus IFU. Also, I think that by now we have a good enough understanding of the effects in the IFU and as well as the slit data that this should not longer be an issue. So if you look at all this again in the full picture, I think all of these points are important to keep in mind and all have effects, but really these huge discrepancies between the findings of no evolution versus a significant evolution, I think that the sample selection is most important, and also the statistics. So let me finish with my conclusions. So I've told you about this tracing the different gases and see how the rotation compares here. And this looks very well, as we've seen, but of course, what we need is more data, and we are currently working on this. Then the evolution of the Tully-Fisher relation I just talked about, and just another thing that we want to do in the future is shown on this plot here. So we want to investigate what are, for example, now the dark matter fractions of progenitors of Milky Way and M31 galaxies. So we've seen these very massive galaxies that evolve into local early type galaxies with similar dark matter fractions, and now we want to see for those galaxies that have lower masses at this higher redshifts, what do we find there? Is the dark matter fraction set early on in the life of a galaxy, or do we find some difference? And this is one of the directions that we are going into now. Thank you. Yes.
In a paper that although was the first author of Peter Beruzzi and others, analyzing a big set of simulations, full phase font, multi-dark font, what we found was that there is a 0-point offset in the maximum circular velocity versus mass relation, which may very well be basically the Tully-Fisher calculation. And that 0-point offset, I think, is consistent with what you're finding. So, at least from a theoretical point of view, we like the 0-point offset.
That's very reassuring.
The paper was published last year. Other side?
I was going to comment about the baryonic dominance in massive galaxies. Again, I think quantitatively, it has to do with the natural transition that galaxies go as they grow from becoming dark matter dominant at the center to becoming baryon dominant due to gas inflow, what I call compaction, due to mergers and so on, that really make this transition. We see it so clearly in cosmological simulations. This is qualitatively, of course, one has to do it qualitatively, but I think this is a natural way. And my prediction is, if you go to smaller, less massive galaxies, 10 to the 9 solar mass, you will find dark matter dominant.
Yeah, exactly. So this is actually your study and the work that you were doing and also showing in the last conferences is what motivated us to now, in the next step, look at these Milky Way progenitors. And if this is feasible and if we can actually determine the outer rotation also in these lower mass systems, we will try to push to even lower masses to test exactly your predictions there. So this is what we want to do at the end.
Except be careful, because these lower mass systems are predicted, at least in the simulations, and appear to be, from the axis ratio distribution, also in the observations, not disks, but instead prolate systems. And it's only after the centers become dominated by ordinary matter, baryons, that they become disks and spheroids.
Yeah, for sure. There you have to take into account also the triaxiality issues and things about that, and have to be very careful about that. That's correct, yeah.
Okay. Any further questions? Yes, Susan Casson.
I don't think we should be measuring the Tully-Fisher relation anymore. Any kind of sample selection on that, like when you look at shorter galaxies, the galaxies that are fairly over, really it's great of a whole other, a large part of your sample. So then you're stuck with kind of an oddly selected sample, and you can do all cells and do a point and stuff. And I'm not sure exactly what that's doing. And you yourself, you can look at a time coefficient, and you know that that means that that's nicely. Into account your so you're looking at the evolution of the whole population, not from oddly selected something that is hard to compare.
Yeah, I fully agree that it's very important to take this into account to get the dynamics right. With the full sample selection, I think it depends. So what you guys are doing is that you really want to see the full population and see how this evolves through time. In this study, we were concentrating more on the original definition of the Tully-Fisher relation to see how the domination rotated systems evolve through time. And I think it's just a matter of how you want to look at things or what exactly you want to study. But for sure, to take into account the pressure support, I think, is really crucial. That's right. Yeah, fully agree.
Okay, let's thank Hannah again.